Okay, so this is AP Podcast 6.1, and we're going to talk about differential rate laws, relative rates when you're looking at reactions, and then the method of initial rates. So for a reaction to happen, this is all review, the molecules have to collide, and they have to collide with enough energy, which is called their activation energy. So there's a set amount of energy they have to collide with in order for those reactions to happen, and that's called the activation energy, and we'll get to that a little bit later in this chapter. They also need to collide with the correct orientation, so they have to hit with the correct atoms striking each other. How are ways that we can increase the rate? An increase in temperature causes molecules to move faster, and we've studied this when we did our inquiry or investigation into reaction rates. So because molecules move faster, there's more energy per collision, so you get more reactions. There's more collisions, and then a rule of thumb is that for every increase of 10 degrees Celsius, the rate's going to double. We can also increase the rate by increasing the pressure. An increase in pressure causes molecules to be closer together, which is going to mean that they're going to collide more frequently. If we shove the molecules closer together, there's a greater chance that they're going to collide, and that they're going to collide with the correct energy and orientation. We can also increase concentration. It's kind of the same thing. More molecules means more collisions, which means the reaction's going to proceed faster. We can add a catalyst. And a catalyst is something that speeds up a reaction, but it's not part of the reaction. What it does, it can either speed it up by lowering the activation energy, so the energy that's required for the reaction to take place is lower with the catalyst, or it can also change the steps of the mechanism of the reaction, and we talked about that a little bit already. Those elementary steps, that's the mechanism. This is showing you a picture of the activation energy. This is without the catalyst, how high it needs to go, and then with the catalyst you can see it drops that jump of energy, that bump right there, that's the activation energy. So with the catalyst it's much lower, so it's faster because it doesn't take as much energy for the reaction to go. We can also increase the surface area, which we tested with the Alka-Seltzer tablets. More surface area means more reactants are available for collisions and you get a faster reaction. All right, moving into chapter 12, it's reaction rates. You can see that the concentration of the reactant decreases with time and the concentration of the product increases with time. So if we're looking here, our reactant is the purple, and then our product is the green. Initially, we don't have any of the product, and that's why it's at 0. And if we look in the beaker at 0 seconds, you can see there's no green. All we have is purple, all the reactants. As this proceeds, the number of molecules, which we can also relate to concentration, is going to drop for the reactants, and it's going to increase for the products. Because as we go through this reaction, we're going to use up the reactants and we're going to produce more products. This is a little misleading. It looks like it goes to completion and stops because all of a sudden at the end here we have no reactant and a whole bunch of product. That is not true in real life. In real life you get to the equilibrium point where the forward and reverse reactions are happening at equal rates, which means your concentrations aren't going to change. Never do you use up completely, or not very often do you use up completely all your reactants and end up with just your products, because there are reverse reactions, and we'll talk about that a little bit later on. Okay, so chemical kinetics deals with the speed at which these changes occur. So we want to know how fast do they go, and that's kind of the reaction rate. The reaction rate of a chemical reaction is defined as the change in concentration of a reactant or product per unit of time. So looking at these formulas right here, here's the rate. It's equal to the change in the concentration. And this A can either be the product or a reactant over a change in time. When you see it written with a negative out here, that's when we're talking about the reactant. Because the reactant's change is going to be a negative, they put a negative out here so that we keep a positive rate. So anytime we're dealing with the reactant being the change in concentration of the reactant, you're going to add in this extra negative sign right in front so it keeps your rate positive. A reaction rate is not constant, it decreases over time. So as we lose those reactants and they start getting converted into products, the rate of the reaction is going to slow down. And that makes sense in terms of, if you think of kind of concentration. As the concentration goes down, we know that the rate also goes down. Relative reaction rates. So if I want to know consumption versus production. So coefficients help determine relative rates of consumption and production. We're consuming the reactants and we're producing the products. Here's our example balanced equation right here. What we do is we can use the coefficients to predict relative rates of these consumption and production. So for example, what I know is that the nitrogen dioxide and the nitrogen monoxide, because they both have a coefficient of 2, that tells me that the nitrogen dioxide is being consumed at the same rate that the nitrogen monoxide is being produced. If I look here at the oxygen, though, it only has a 1 for a coefficient. So how I would relate that then is that I know that the nitrogen dioxide is being consumed twice as fast as the oxygen is being produced. And you can use those coefficients to kind of do the relative rates of consumption and production. And that's what we use those coefficients for. So our example here gives us our equation. It says, what is the relationship between the rate of production of ammonia and the rate of consumption of hydrogen? So we're looking at ammonia versus hydrogen. And the ammonia has a coefficient of 2, and the hydrogen has a coefficient of 3. So it wants the rate of production of ammonia. And since ammonia has a smaller coefficient, it should be slower. So we should be producing ammonia slower than we're using up the hydrogen. And how much slower is just the ratio of the coefficients. So what we would say is that ammonia is being produced 2/3, because that's going to be slower. 2/3 as fast as hydrogen is consumed. So in relationship to ammonia versus hydrogen, the ammonia is being produced 2/3 as fast as hydrogen is consumed. If we look in relationship of nitrogen to ammonia, the ammonia is being produced twice as fast as the nitrogen is being consumed. So again, just looking at the ratio of the coefficients helps us determine the relationship between the rates of production and consumption. All right. The thing to know, and this is what we were talking about earlier on that slide where the concentrations were changing over time. It says chemical reactions are reversible. As products build up, the reverse reaction becomes important. So as we start building more and more of our products, it actually starts the reverse reaction. So initially, this might be our forward reaction. But as the nitrogen monoxide and the oxygen start building up, there comes a point when they come together and they start going back into forming what we would say was the reactant. So the forward reaction occurs, and then as these build up, then all of a sudden we start seeing that reverse reaction. When the rates of these are equal, that's when we're at an equilibrium. But it is important to note that the reverse reactions become important the longer these reactions are let go. If the time gets longer, then the reverse reactions become more important. So in order to avoid complications, we usually choose to study a reaction soon after the reactants are mixed, before the products have time to build up. We want to do this as close to t equals 0 seconds as possible. So we want that initial instantaneous reaction rate. Right when we mix them, what happens? That allows us not to have to worry about the reverse reaction. It's more true to what's going with just the forward reaction, which is usually what we're studying. We like to write rate laws when we're looking at these reactions. So the rate law equation in general is the one you're seeing right here. The example one, this is written from here. The rate law equation is always in terms of the reactant, or sometimes the reactants. It just depends on what your balanced equation looks like. In this case, since there's only one reactant, we only have one here. So the rate is equal to K, and K is a rate constant. It's specific to this chemical equation. The concentration of our reactant, and N is the order of the reactant. K and N have to be determined experimentally, so it's not something that you can just look up in a table. It's something you have to use data and you have to figure out what it is. N cannot be written from the reaction. So just because there's a 2 in front of the NO2 here does not mean that the N here is 2. It could be a 1, it could be a 3. It is going to be a positive integer, but you don't know what that is without looking at some data. So this is the general format for a rate law. If it had 2 reactants, you would see it look like this. We'll call this A. So that's reactant A. This might be reactant B. And then they would put an M there for that order because they're going to be different for each reactant. So this one, you have one reactant in the rate law. This would be a 2 reactant equation, and you would have the 2 different reactants right there. The concentrations of the products do not appear in the rate law because the reaction rate is being studied under conditions where the reverse reaction does not occur. So that's just saying that we don't put the products, we don't put the concentration of the products in. If we look back at this one, we are focusing only on the reactants because we're looking at only the forward reaction. That instantaneous time right after we mix them is what we want to know, so we don't care about the products. This is what we care about. All right, the 2 types of rate laws, and we're going to talk about the differential rate law today. The differential rate law, which is also just called the rate law, shows how the rate of a reaction depends on concentrations. And that's the one that we just wrote down because it had concentration in the formula in the equation. The other type of rate law is called the integrated rate law, and we're going to get to that later. It's different because it shows us how the concentration depends on time. So this one is how the reaction rate depends on concentrations. This is how the concentrations change versus time. So this is the one we're focusing on now. We'll get to this one later. In order for us to determine the rate law, so that differential rate law, we use what's called the method of initial rates. And the method of initial rates is where we take several experiments and we carry them out, and we take the initial rate for each run, and then we put it in a table and we can compare those initial rates and see how they are affected by the initial concentrations of the reactants. And it's a little easier if you can look at a table to see what we mean. So here's what we have. This is our practice problem. It's our table. You have it in your handout. It says the initial rates from 3 experiments for this reaction are right here. So we were focusing on changing the concentration of the ammonium ion and changing the concentration of the nitrite ion. And that's what we have here and here. What they wanted to do is they wanted to change one at a time. So for example, if I look at experiments 1 and 2, they held the ammonium ion concentration constant while doubling the nitrite ion concentration. What that does is it allows us to see if we double the nitrite concentration, what happens to the rate. And you can kind of see here that it doubled. As I doubled the rate, as I doubled the concentration of the nitrite ion, it made the reaction go twice as fast. So that's experiments 1 and 2. Then if I look at experiments 2 and 3, I held the nitrite constant, but I doubled the ammonium ion. So the ammonium got doubled, it went from 0.1 to 0.2. And if we look at the rate, it also doubled. So as we doubled the ammonium ion concentration, we also doubled the rate of the reaction. And now they're all not this easy to kind of pick out, and I'm going to show you mathematically how we do this. And it's a pretty long problem, so write kind of small. All right, so the first thing you want to do when we do this is we want to pick our pair of experiments that we're going to focus on where they're changing just one of the reactants. So if I were doing this, first of all, I'm going to write the rate law. Rate would be equal to K, the rate constant, times the ammonium ion concentration to the nth power, and then we have the nitrite ion concentration to the nth power. So there is our general format. We're going to solve for the N, we're going to solve for the M, and we're going to at the end solve for K, and we're going to be able to find all of that information by just using what they gave us in the table. So the first thing I'm going to do is I'm going to focus on the ammonium ion concentration. And with the ammonium ion concentration, we said that was 2 and 3 because that's where they changed the ammonium, they held the nitrite constant. What I do is I just plug it in to this formula right here, all the information that I know. And I'm going to put experiment 3 on top and put experiment 2 on the bottom. And this will make more sense after I plug it in. The reason I'm doing it this way though is because I like to end up with whole numbers. You could do it the other way and it would be just fine, but I like it this way because I end up with a whole number. I want the big rate on top. I want the larger rate to go on top. So I plug this in. I have 5.4 times 10 to the negative 7th is equal to K. I don't know K yet. I do know that my concentration of ammonium is 0.2. I don't know N. I know that my nitrite is 0.01, and I have M. So that's experiment 3's information. Then I plug in experiment 2. Experiment 2's rate is 2.7 times 10 to the negative 7th equals K, and that one is 0.1 molar for the ammonium, still to the nth power, and this one is 0.01 still to the nth power. Okay, so if I look at these, the first thing I want to do is look for what cancels. And my K's, even though I don't know them, I know they're going to be the same and they're going to cancel out. These guys are going away because they're the same. What I'm left with is the rate right here is equal to dividing these two. So if I take 5.4 times 10 to the negative 7th and I divide it by 2.7 times 10 to the negative 7th, I get 2. So 2 is equal to 0.2 divided by 0.1 is 2, and then I still have my power of n there. So I have to think 2 raised to what power gives me 2, and that tells me that n is equal to 1. So n in our rate law is going to be 1. And now I'm going to do the same thing, but now I'm going to focus on the nitrite because that's going to let me solve for m. So I'm going to erase this, and now I'm going to look for m. So in this case, I want to hold the ammonium constant, so I'm going to look at those two because that's where we're changing the nitrite. Again, I'm going to put the larger rate on top because I like ending up with whole numbers. So I'm going to put experiment 2 on top and experiment 1 on the bottom. I start with the rates, so 2.7 times 10 to the negative 7th is equal to, I want to do the ammonium first still, so 0.1. And even though I know what n is, I'm just going to leave it as n because it's all going to cancel out anyway. And then my m for this one is 0.010, and I have m. And then underneath that I put experiment 1, 1.35 times 10 to the negative 7th is equal to 0.100, and that's my ammonium. And then my nitrite is 0.005. So again, these that are identical, they're going to cancel. I forgot my K's, but they're going to cancel. So they're in there as well. And then when I do this math, 2.70 times 10 to the negative 7th divided by 1.35 times 10 to the negative 7th is 2. And that's equal to, if I take 0.01 divided by 0.005, I get 2. And there's my power of m. So 2 raised to the first power again is going to give me 2. That means m is also not 2, but 1. So m is 1. That means that we found out that the order of the reactant of ammonium is 1, and then this order of the nitrite is also 1. So if I want to rewrite my rate law equation with what I know, I would say rate is equal to K, because I still don't know what K is, the concentration of the ammonium ions, and there's a 1 there, but I don't have to write it because it's 1. And then I have my nitrate ions, and again, there's a 1 there, but I don't have to write it. So we found a little more information here, and we can plug it into that rate law. The next thing you need to be able to do is figure out the overall rate law, the overall order. overall order of the reaction. And what you do with that is you just add up your powers. So 1 plus 1, the overall order for this reaction would be a 2 because we just add up the powers of those reactants. So there's that. And the last thing we want to do is we want to find the value of K. So in order to find the value of K, K stays the same. It's a constant. That means I can pick any of these experiments and I can plug in the information and still get the same value for K. So I'm just going to go ahead and I'm going to pick experiment 1 just because it's at the top. So what you do is you plug everything in and you have to be conscious of the units because K's units can change depending on the orders of the reactants. So K does not always have the same units. You have to calculate them each time. So for this one, experiment 1, we have 1.35 times 10 to the negative 7th moles per liter second is equal to K. My concentration of my ammonium is 0.100, and instead of molar, I'm going to write out what it actually is, which is moles per liter. And then it's to the first power, and this one is 0.005 moles per liter. So what you would do is you would take those two and you're going to multiply them together. So we end up with K, and then if I multiply those two together, I get 0.0005, and a mole times a mole is mole squared, and a liter times a liter is a liter squared. So I can ignore this now. In order to get K by itself, I have to bring this side over. I have to divide by that. So I'm going to have my 1.35 times 10 to the negative 7th moles per liter second, and I'm going to multiply it by the inverse of this. I'm going to flip it over. So my liters squared is going to be on top, and my number with my moles squared is going to be on the bottom. And that's all equal to K. So what I'm going to find out here is my liter is going to cancel with that, leaving me just 1 liter on top. My mole here is going to cancel the squared out, so I'll be left with a mole there, and my seconds are going to stay on the bottom. And when I multiply that together, I get 2.7 times 10 to the negative 4th, and then I just bring over all my units. So I have a liter on top per mole second. And that's your answer for K. So the rate constant for this reaction is 2.7 times 10 to the negative 4th liters per mole second. You can tell then from just this information we are able to calculate a whole lot of information about this reaction. We can find the orders of the reactants, we can find the rate, constants of value, we can find the overall order of the reaction. So a lot of information can come from just them providing you with a table like this. All right, that is all we're going to do on the podcast. We're going to do a lot more in class, though, together. We're going to do another practice problem with the method of initial rates. So bring your notes, bring any questions that you have, and I will see you in class.